Good morning, everybody. At first, introduce myself. My name Puku Setio Pratomo, come from Chemical Engineering Department, the University of Surabaya. In this conference, I would like to share my recent work, research titled Rheological Behavior and Antioxidant Activity of Carrageenan extracted from green seaweed, Eucheuma cottonii, using alkaline solution at low temperature. My presentation will include several parts, that is background, objective, extraction step, research, and conclusion. What is Carrageenan? Carrageenan is an additive used as thickener, emulsifier, gelling, texturing, and suspending agent. It's a natural ingredient that's come from seaweed. We also often find this ingredient in nut milk, meat product, and yogurt. This picture on the left side is the seaweed as a raw material, while the picture on the right side is the Carrageenan as the product. Chemical structure of Carrageenan. Carrageenan has three different chemical structure, which are known as kappa, lambda, and iota structure. These three types of Carrageenan are distinguished based on difference in cell binding, gel properties, and protein reactivity. Kappa Carrageenan is produced from Eucheuma cottonii, soluble in hot water and easily form a gel in water. Lambda Carrageenan is produced from Composites, while iota Carrageenan was produced from Eucheuma simonosum. Kappa Carrageenan produces the strongest gel properties, while lambda does not form a gel in water. But lambda Carrageenan interact well with protein, so that this type is suitable for food production. Meanwhile, iota Carrageenan form a strong gel in an acid solution. Nutritional content of seaweed. The slide shows that the nutritional content of seaweed, which show that seaweed contain many nutritional components that are needed by the body. Besides being source of calorie, it's also contain protein, vitamin, and various minerals. As the largest maritime country in the world, Indonesia has many seaweed cultivation centers spread from the west to the east of Indonesia. However, as shown in the map, the largest center for seaweed cultivation is in eastern Indonesia, covering Sulawesi, Maluku, and West Papua. This table shows Indonesian seaweed production in recent years, with total production ranging around 10 up to 11 million tons per year. With total production of about 11 million tons per year, Indonesia is the second largest seaweed producer after China. Taking into account the great potential of seaweed resource in Indonesia, in the research work, seaweed is processed into Carrageenan by extraction using sodium hydroxide and potassium hydroxide solution. The experimental variable is the alkaline volume to mass of the seaweed ratio. It will be 30, 35, 40, and 45 milliliter per gram. There are four research objectives in the study. The first objective is to investigate the yield of Carrageenan. The second objective is to observe the rheological behavior of the Carrageenan extract. The third objective is to observe the antioxidant activity of the Carrageenan extract. And the fourth objective is to observe the effect of alkaline type of the yield, the effect of alkaline type on the yield, the rheological behavior, and the antioxidant activity of the Carrageenan extract. The extraction step is expressing in this figure. The first step is to wash and to soak the fresh seaweed in tap water. Soaking is carried out for 24 hours to separate impurities. After that, the seaweed is separated by filtration and then dried in oven at 30 degrees Celsius for 24 hours. The next step is to cut the seaweed into smaller size before addition of alkaline solution and let the extraction process occur at 30 degrees Celsius for 1 hour. After the extraction was complete, the insoluble solid are separated by filtration, and the separated liquid is Carrageenan extract. KCl salt solution was then added to the Carrageenan extract to form gel. The gel form was then dried in an oven at 30 degrees Celsius for 16 hours before being analyzed to observe the rheological behavior and the antioxidant activity. Now, the result. The first is about the Carrageenan yield. The figure on the slide shows the yield of the Carrageenan. Carrageenan yield is the ratio between the dry mass of Carrageenan obtained and the mass of seaweed juice. From the figure, it can be clearly seen that the yield of Carrageenan increased with the increasing ratio of solvent volume to mass of fresh seaweed. The extraction result also shows that the use of potassium hydroxide solution produce a higher yield of Carrageenan than the sodium hydroxide solution. The highest yield of Carrageenan was obtained by extraction with potassium hydroxide sulfate at a solvent volume ratio of 45 milliliter of potassium hydroxide per gram of seaweed solution, which was about 33.4%. The rheological behavior. Rheological behavior of the Carrageenan represented as correlation between shear stress and shear rate as shown in the picture. This result indicated that Carrageenan extract using potassium hydroxide solution produce higher shear stress than Carrageenan extract using sodium hydroxide solution. This implies that the extraction with potassium hydroxide solution produce a more viscous Carrageenan solution than those extracted using sodium hydroxide solution. The higher the ratio of the volume of the solvent to the mass of seaweed, the greater the viscosity of Carrageenan was indicated by its higher shear stress. In this recent work, two rheological models were observed for their suitability with the experimental data, namely the Bingham model and the power law model. Referring to the value of the determinant of coefficient generated from the two models, it demonstrated that rheological behavior of the Carrageenan was more fitted to the power law model. This proved that the Carrageenan extract is in water form a non-Newtonian fluid. Well, in general, by investigating all of the rheological behavior present in the feature, it showed that the magnitude of the shear stress was not very sensitive to the change in shear rate. This was of an advantage of this product related to the energy consumption due to the occurrence of shear force in the process using this product. antioxidant activity. There is a growing interest for antioxidant due to the need to prevent cell damage in the human body due to the activity of free radical compound. Although the human body was able to produce its own antioxidant, additional antioxidant was still needed because the antioxidant in the body were often unable to neutralize all of the existing free radical compound. Antioxidants were also needed to prevent the deterioration of fat and other food ingredients. For that purpose, natural antioxidants were preferred compared to synthetic antioxidant because they tend not to cause adverse side effects. Thus, utilizing seaweed as an alternative source of natural antioxidants seemed to be a promising prospect. In this study, the DPPH method was used to determine antioxidant activity. The result demonstrated that carrageenan extracted with an aqueous solution, sodium hydroxide sulfate, produce a higher percentage of DPPH, radical scavenging activity than those extracted with potassium hydroxide sulfate. AC50. Antioxidant activity was also commonly expressed as IC50, which was the concentration of sample capable of scavenging 50% of DPPH. The IC50 value was inversely proportional to the antioxidant activity. Sample with higher IC50 had lower antioxidant activity. This result showed that carrageenan extracted using sodium hydroxide sulfate demonstrated lower IC50 value, thus having higher antioxidant activity. The IC50 value of the sodium hydroxide extract were in the range of 0.2 up to about 30 ppm, indicating a potent antioxidant activity of the carrageenan extract. The conclusion. First conclusion, extraction with potassium hydroxide solution produce a higher yield of carrageenan than using sodium hydroxide solution. The highest yield obtained is 33.4%. The second conclusion, rheological behavior of the carrageenan extract followed the power law model and the stress was not very sensitive to the change in shear rate. The third conclusion, the carrageenan extract obtained using sodium hydroxide solution had a higher antioxidant activity than those obtained using potassium hydroxide solution. And the last conclusion, the IC50 value of the sodium hydroxide extract were in the range of 0.2 up to 30 ppm, that indicating a potent antioxidant of the carrageenan extract. Carrageenan product photograph. The left side photograph is the carrageenan gel, where the right side is the carrageenan dry powder produced in the research book. Thank you.
Good morning, ladies and gentlemen. I would like to present my paper entitled A Performance Study of Magnetite-Lignin Composites as Photothermal Materials in Solar Steam Generation System by Marta de Vega Eucheuma, Widya Stuti, Nibadi Intan, and Heris Setiawan from 10 November Institute of Technology. Well, we chose this topic because of the condition of our country nowadays. The clean water scarcity still become a global issue which threatens numerous people in Indonesia. Even though Indonesia is an archipelago country that has the second longest coastline in the world, Indonesia was still in the red zone in the report on one of the Sustainable Development Goals. that ensuring that people achieve adequate access to clean water and sanitation, which means that the fulfillment of clean water and proper sanitation was still a major challenge in Indonesia. Seawater desalination is considered to be the main solution to this water crisis problem in maritime countries like Indonesia due to the ability to produce abundant clean water for domestic and industrial usage. However, the consumption of electrical energy in this desalination process is very high, which results in water loss and emissions of greenhouse gases. In addition, it may harm the growth of marine life during the process of taking seawater and removing high salinity seawater. Another disadvantage is this salination process cannot be carried out in some areas that do not yet have electricity and centralized water desalination, whereas these areas are in urgent need of clean water supply. Recently, a new strategy which may suitable for tropical countries in the production of fresh water, which demonstrate the high evaporation capability of seawater, named solar steam generation or SSG, has been developed. The concept of clean water produced by utilizing solar power is believed to be able to solve problem of the clean water crisis in a country with high light intensity such as Indonesia. In the SSG concept, several attempts have been made to increase photothermal efficiency by increasing light absorption and minimizing heat loss. Recent developments in SSG place photothermal materials, which is materials that act as a converter of light energy to thermal energy, at the air-water interface, thus supporting only a fully aerated air-liquid interface, resulting in higher photothermal efficiency. One of the key of the SSG device is a photothermal material which acts as a sunlight absorber because the evaporation performance with the help of sunlight is determined by the properties of this material. For this reason, high light absorption capabilities across the full solar spectrum and high light energy to heat conversion efficiency are major considerations in photothermal material design. To date, photothermal materials such as plasmonic metals, semiconductors, carbonaceous materials, and polymers have been studied as key elements in increasing water evaporation, but unfortunately, these photothermal materials are usually difficult to separate from water, resulting in loss of active ingredients, and more importantly, they will lead to significant water pollution. Although the use of the support substrate as a flotation system allows materials recycling, this often lessens the evaporation efficiency. In addition, the presence of supporting materials such as airlaid paper and gauze cannot ensure close contact with the water surface, resulting in suboptimal use of photothermal materials. So, in this study, we focus on the performance of magnetite photothermal materials, which have favorable magnetic properties. This magnetic material may be easily separated using magnetic field for reuse and has low toxicity and an easy and low-cost synthesis method. Therefore, it can be the answer to the shortcomings of other photothermal materials. In improving materials recycling, magnetite also has a high thermal conductivity, making it possible to use it as a photothermal material with high solar thermal conversion performance. And the and the help of lignin can make this material be safe float on the water surface. In 2011, Zhang et al. Have investigated the performance of magnetite carbon as photothermal material and conclude that composites could evaporate water in the rate up to 2.3 liter per meter square per hour under intensity of almost 100 watt per meter square. But there are several materials dispersed in the system. And then Chen et al. Um, studied about the performance of magnetite as solar absorber that could evaporate and up to 3.44 liter per meter square hour water. Then Chen et al. Continued the study about magnetite carbon as photothermal material, which resulted that it had evaporation rate of 1.07 kilogram per meter square per hour under intensity of 1 kilowatt per meter square. But the evaporation rate is lower than the previous study. The magnetite nanoparticles were synthesized by an electrochemical method following by our proposed procedure. Typically, the iron electrodes were immersed in 2,200 milliliter demineralized water. The pH of the electrolyte was adjusted to 9 by adding 2 molar of natrium hydroxide. The electrodes were arranged into 4 rows, where each row consists of 2 electrodes separated by 2 mm to avoid electrical short circuit. Then the electrodes were installed in an alternating monopolar configuration, and each electrode was individually connected to the positive and negative terminal of the DC power supply. Obtain the self-floated material, the synthesized magnetite nanoparticles were composited with lignin by grinding a predefined proportion of magnetite and lignin in a mortar. And then we characterize the obtained particles. The first one is XRG analysis to identify the nanoparticle form, and then hydrophobicity to investigate the hydrophobicity of each material, and the next is the light absorption capability of particle was measured by spreading a certain amount of particle on the bottom of beaker glass, and the absorption of light was measured by a quantum meter. And then the water evaporation experiment were conducted at room temperature by use a LED lamp that applied as the light source, and a quantum meter was used to measure the light intensity, and the distance between the lamp and the water surface is 6 centimeter. The experimental setup is shown by this figure. After the sample preparation, we obtain this result. During the electrosynthesis of magnetite nanoparticles, the electrolyte was initially clear. After several minutes of electrolysis, yellow-brown color appeared indicating the formation of ferrodihydroxide. Then, the color of the precipitates moderately changed to reddish-brown, indicating the formation of FeOOH. Finally, the precipitates became black, indicating the formation of magnetite. This mechanism of particle formation was corresponding to the mechanism reported by Fajera et al. In the previous study. The black precipitates were then separated from the electrolyte solution and then dried in an oven at 80 degrees Celsius for 12 hours. The photo of obtained black nanoparticle is shown in that picture. To identify the nanoparticle form, an XRZ test was carried out so that the following results were obtained. The diffraction pattern had 4 peaks which were matched well with the standard peaks of magnetite. To evaluate the properties of magnetite to water, a hydrophobicity test was conducted. Hydrophobicity was measured in terms of the contact angle of the water drops to the surface of magnetite nanoparticles. The contact angle greater than 90 degrees was supposed to be hydrophobic. The water drop tended to spread out and weighted the surface of magnetite nanoparticles. This result indicated that magnetite nanoparticles were hydrophilic. This made the magnetite impossible to float on the water surface. Meanwhile, the contact angle of magnetite, which was composited with lignin particle, was performed as this figure. It exhibited that magnetite-lignin composites had a water contact angle of more than 90 degrees, which meant that the composites were hydrophobic. Due to the existence of lignin particles, their hydrophobic surface generated surface tension and additional buoyancy made the magnetite nanoparticles to float on the water. To investigate the light absorption capability of magnetite-lignin composites, various amounts of those were spread evenly on the bottom of a beaker, and the radiation intensity of the simulated sunlight was measured. The radiation intensity decreased from 532 watt per meter square to 522 watt per meter square after the sunlight passed through the empty beaker, indicating that 10 watt per meter square was absorbed by the beaker. It was significantly reduced from 522 to 28 watt per meter square when 0.2 gram of magnetite-lignin were spread uniformly at the bottom of the empty beaker. When the amount of these composites rose to 1 gram, the radiation intensity further dropped close to zero. To obtain better understand about the enhanced solar evaporation system, during the water evaporation process, the surface of water temperature was monitored, and the results are shown in that figure. The surface temperature of water without any photothermal materials increased slightly in the 2 hours from 28 degrees Celsius to 45 degrees Celsius. Meanwhile, with the addition of magnetite nanoparticles on the water surface, the water surface temperature reached 51 degrees Celsius. However, the magnetite-lignin composites show the most expected result of the photothermal material, which was able to enhance the surface temperature of water from 28 degrees Celsius to 56 degrees Celsius. Due to the hydrophilic properties, magnetite nanoparticle did not have self-floating ability to lessen the heat loss because of the existence floating substrate. The magnetite nanoparticles were modified by adding the lignin particles so that they were able to float on the water surface. To understand the effect of self-floating ability to the performance of material as photothermal agents, magnetite and modified magnetite were compared in terms of water evaporation with the setup as shown in that figure. The result of the water evaporation test of the magnetite and modified magnetite presented in the graphic, and the water evaporated without using any photothermal material reached only around 1 liter per meter square after exposure to sunlight for 2.5 hours. But when the number of magnetite nanoparticles was added to the system, the water evaporated reached to 2.5 liter per meter square, and this was due to the ability of magnetite nanoparticles to localize heat from sunlight simulator and then used to escalate the temperature of water surface and evaporate water. However, the addition of supporting substrate could not reduce the heat loss, and this was proved by the volume of water evaporated enhanced up to 4.5 liter per meter square because of the addition of magnetite-lignin composites nanoparticle, which were able to self-float on the water surface. So, we can conclude that magnetite nanoparticles have been successfully synthesized using electrochemical methods. The obtained magnetite could raise the volume of water evaporated up to 2.53 liter per meter square in the 2.5 hours under the sunlight simulator. Compared with no material system, this system showed greater performance of water evaporation. But, however, the best performance of water evaporation exhibited by the hydrophobic magnetite-lignin nanoparticles, which were able to evaporate up to 4.5 liter per meter square water in the same time range. Well, that's all from me. Thank you for the attention.
Hello everyone, let me introduce myself. My name is Diana Novitasari. You can call me Diana. Now, I will present my research entitled Organosolv lignin from coconut coir as potential biomaterials for sunscreen. This research was compiled by Diana Novitasari, Mahardika Efrois, Widya Stuti, and Heru Setiawan. We come from Department of Chemical Engineering, Faculty of Industrial Technology and System Engineering, 10 November, Institute of Technology, Surabaya, Indonesia. The outline of this presentation is: first, introduction; second, the experimental methodology; third, the result and discussion; finally, the conclusion of this research. Now, We will discuss about introduction. In the introduction, we will explain the background of this research. Namely, lignin is the main constituent component of plant cell walls, which plays an important role in maintaining the stiffness and strength of stems, makes cell walls waterproof, and plays a role in protecting plants from pathogens. The existence of lignin is very abundant in nature, since lignin is the second largest polymer component on Earth after cellulose. The production of lignin in nature is up to 360 million tons per year, whereas in the pulp and paper industry alone, more than 50 million tons of lignin are produced as a byproduct each year. However, less than 2% of industrial lignin is used commercially for low-value applications as considered additive, dye dispersants, surfactants, and pesticides, while the remainder is used as factory fuel. This is due to the complex, varied, and difficult to degrade lignin structure. Therefore, significant attention has been paid to the use of lignin byproducts to become value-added products. Besides being abundant in nature and inexpensive, the structure of lignin, which contains aromatic rings of methoxy and hydroxyl groups, causes lignin to have high antioxidant properties. Besides that, lignin also contains ultraviolet light absorbing functional groups such as phenolics, ketones, and other chromophores. Due to the nature of lignin that can absorb UV light, lignin can be used as a sunscreen agent. But previous studies still make lignin from materials that are not environmentally friendly and harmful to the skin, causing allergic reactions to the skin. The previous research from this experiment is on 2015. Qian et al. Synthesized lignin with an alkaline process, which is then purified by adding an acid. Then the alkali lignin is added to several commercial sunscreen products. The results show that adding 2% lignin could increase the SPF value of sunscreen from SPF 15 to SPF 30. The addition of 10% lignin increased the SPF value of sunscreen from SPF 15 to above SPF 50. On 2017, Qian et al. Synthesized the enzymatic hydrolysis of lignin and organosolv lignin, which is then purified by dissolving alkaline, acidification, filtration, and washing, then mixed with skin cream as a lignin-based sunscreen. The results showed that the lignin-added skin cream had better sunscreen performance. Furthermore, the SPF value on the sunscreen decreased because of lignin particle size. Next, we will discuss the methodology of this research. The materials used in this research are: first, coconut coir was collected from a local market in Keputi, Surabaya, Indonesia. Then, ethanol and demineralized water were purchased from UD Sumber Ilmiah Persada, Indonesia. For analysis, sulfuric acid was purchased from MEG. All chemicals were of analytical grade and used as received without further purification. The methodology for this experiment is: lignin from coconut coir was extracted using an Organosolv method. Prior to extraction, the coconut coir was ground in a milling machine to obtain a smaller size, from 25 mS to 40 mS. The ground fibers were then digested in ethanol 58% at its boiling point under atmospheric reflux for 5 hours. The digestion was conducted at a volume ratio of 20 ml of ethanol per gram of coconut coir. After the pulp was separated by filtration, The Organosolv lignin was characterized for its UV absorbance. As for the characterization that has been carried out, namely, Fourier transform infrared spectroscopy to determine the functional group of lignin, and then UV spectrophotometer to determine the absorbance value of lignin. Next, we will discuss about the results and discussion of this research. The lignin content in the coconut coir is dependent on the maturity of the coconut fruits. Therefore, the effect of coconut maturity on the lignin content was studied first using the Cheson method. Table 1 shows the lignocellulose content of mature and green coconut coir before and after the lignification. In the original coconut coir, the lignin content of mature coconut coir was higher than that of green coconut coir. This may be caused by the formation of secondary cell walls in mature coconuts, which are composed of lignin compounds. From Table 1, it seems that lignin in mature coconut coir is easier to extract using the Organosolv method. As shown in Table 1, the decrease in lignin content of mature coconut coir is approximately 12.6% higher than that of green coconut coir, which is only 6.91%. This may be caused by the higher content of moisture in green coconut coir. The higher water content may hinder the direct contact of ethanol and lignin that makes ethanol not attack lignin effectively. This differs from the case of mature coconut coir, where the moisture content is relatively low. Hence, ethanol can directly attack lignin in the coconut coir. The IR absorption spectra of the ethanol 50% and Organosolv lignin solution studied were recorded in the 650 until 4000 per centimeter region, as shown in Figure 1. In ethanol 50% has OH, CH, and CO bonds. For Organosolv lignin has OH, CH, C double bond O, C double bond C, and CO bonds. The difference is indicated by the presence of C double bond O bonds indicating a carbonyl group and C double bond C bonds indicating an aromatic ring in the Organosolv lignin solution, while in the ethanol solution it doesn't have that bond. The results of UV spectrophotometry analysis of Organosolv lignin solution with various concentrations are shown in Figure 2. The wavelength studied were UVC at wavelength 200 until 290 nanometers, UVB at wavelength 290 until 320 nanometer, and UVA at wavelength 320 until 400 nanometer. From Figure 2, it can be seen that for UVC, the UV absorbance value increased with increasing lignin concentrations. For UVC at all concentrations, there was an increase in the absorbance value at a wavelength 250 nanometer and that a constant until at wavelength of 290 nanometer. The increase in absorbance value may be because the chromophore structure in lignin can absorb effectively at the wavelength. For UVB, the absorbance value was increased when the lignin concentration increased. At a wavelength of 290 until 320 nanometer, the absorbance value decreases when the lignin concentration is low, namely 500 until 700 ppm. However, when the lignin concentration is high, namely 800 until 1500 ppm, the absorbance value remains constant. For UVA, as well as UVB and UVC, the absorbance value also increases when the lignin concentration increases. For UVA, at a concentration of 500 until 800 ppm, the absorbance value decreases, while at a higher concentration, 900 until 1500 ppm, the absorbance constant then decreases. The higher the lignin concentration, the more constant the absorbance value. From Figure 2, it can be seen that the Organosolv lignin solution has the highest absorbance value at a wavelength of 250 nanometer to 290 nanometer, so it is very effective at absorbing all UVC. For UVB and UVA, the absorbance value decreases with increasing wavelength. For UVB, the absorbance value is still above 1, so it is still effective for absorbing UVB. For UVA, only concentration above 1000 ppm can absorb all UVA, which is characterized by absorbance value above 1. A concentration of 500 until 900 ppm only absorb part of the UVA because the absorbance value is below 1. The physical appearance of the Organosolv lignin solution is shown in Figure 3. From Figure 3, it can be seen that for a concentration of 500 until 1000 ppm, there is a color change from the brownish yellow to brown. At a concentration of 1100 until 1500 ppm, it is dark brown. From Figure 3, it can be seen that the color of lignin gets darker as the lignin concentration increases. However, the color change shown is not too significant. In this study, a concentration of 1000 ppm was optimal because the color was not too dark and the absorbance value was above 1 for all UV. Last, we will discuss about the conclusion of this research. The conclusion of this research is Organosolv lignin has been evaluated as a natural sunscreen agent. As expected, Organosolv lignin can absorb ultraviolet light. The higher the concentration of lignin causes the absorbance value to increase, so that the ability to absorb ultraviolet light is more effective. However, the high concentration of lignin causes the color to darken. Therefore, an optimum concentration of Organosolv lignin is required to absorb all ultraviolet light. The optimum concentration obtained was Organosolv lignin with a concentration of 1000 ppm. This work demonstrates the value-added application of lignin for cosmetics. That's our presentation. Thank you for your attention.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Let me introduce myself to you. My name is Ratris Karinggalih and I'm from 10 November Institute of Technology. Now, I want to represent my research to you. The title is The Effect of Sodium Lauryl Sulfate on Silica Nanofluid Stabilization using Microbubble method. This research by Ratris Karinggalih, Imade Joni, Widya Stuti, and Heru Setiawan. First, the background of this research is we know there is so much source of nanofluid in this world. The one of source is silica. Silica was chosen because of its controllable properties and good stability under certain conditions. And the best form is colloidal silica. And then there are various synthesis methods, but the most widely used are synthesis colloidal silica by inorganic materials such as calcium hydroxide or hydrochloric acid. But the use of inorganic materials is not environmentally friendly. So that in this research we propose carbonation process using carbon dioxide gas. And the purpose of this research is to develop silica surfactant stabilized nanofluid from sodium silicate by carbonation in a microbubble column at atmosphere condition. Bubbles can classify in many ways. One of them is by their size. The first, there is millibubbles, which have diameter larger than 100 micrometer. And then there is microbubbles, which have diameter between 1 micrometer to 100 micrometer. And the last one is ultrafine bubbles, which have diameter less than 1 micrometer. And then for this research we use microbubbles. We use previous research in this work. One of them is by Chai et al. In 2009. The title is Synthesis of Silica Powders by Pressured Carbonation. And the result is find the best condition is PEG surfactant 5% in pressure conditions. And the next one is by Comaria et al. In 2018. The title is Preparation of Stable Colloidal Silica with Control Size Nanospares from Sodium Silicate Solution. The result is synthesis colloidal silica by sol-gel method with controlled size. And Comaria use calcium hydroxide for synthesis. And in this research there is so much luck. One of them is use inorganic materials and then in pressure condition, which cannot save energy use. And this is a schematic diagram of microbubble reactor. The carbonation process, the first is the sodium silicate solution with a concentration of 0.5% was pumped into a glass column. The 0.5% sodium silicate solution was prepared by diluting the 28% sodium silicate solution with demineralized water. Sodium lauryl sulfate was also added into the solution during its preparation with a 5 critical micelle concentration. When the solution reaches a certain height, it will flow into the fine bubble generator. Carbon dioxide gas and the solution will come into contact thus the carbonation process occurs. Then, the solution is pumped back into the glass column to prolong the contact time between the solution time and carbonation gas, where this process will continue until it overflows. The solution flowed out of the gravity tank as a final product, then evaluated with many kind parameters of stable nanofluid. One of them is pH measurement. The process was continuous because flow rate of the sodium silicate solution was fixed constant as in slide we can know. The step of synthesis process of silica SLS nanofluid is the first, mixing sodium silica solution 0.5% and SLS 5 cmc for about 30 minutes, and then it's called precursor solution. Then the precursor solution is used for carbonation. Carbonation of the solution is carried out in a batch process and in its atmosphere condition, and then it forms silica SLS nanofluid. Finally, silica SLS nanofluid can analyze and characteristic of nanofluid stability. And the next chapter is the result and discussion. And then this physical appearance by the time of nanofluid. The first is silica nanofluid and silica SLS nanofluid for a day. We can observe that the color is clear and there's no sediment, and it can be indicated that silica nanofluid and silica SLS nanofluid are still stable, and we want to know stable for this nanofluid, and then we observe this nanofluid after a month, and then this comparison of silica SLS nanofluid and silica nanofluid after a month, and then there is still no color, and then there is no sediment. And then from a physical appearance, we know that nanofluid is still stable, but we have to check the pH level, because the pH level is an important factor affecting the stability of nanofluid. And then this comparison table of silica SLS and silica nanofluid for a 5 day. And we know that for the nanofluid without SLS, the decrease approximately is 3%, and for silica SLS is only 1%. The lower decrease in pH with time may indicate that the silica nanofluid with SLS is stable than without SLS. The decrease in pH may be caused by the condensation reaction of surface silanol groups with the remaining orthosilicic acid in water. And this is a reaction that occurs in this phenomena. And then the presence of surfactant in the solvent may hinder the direct contact between the surface silanol groups and the orthosilicic acid. This may be the reason why the pH of silica nanofluid with the presence of surfactant only decreased slightly. And then from a physical appearance, we know that nanofluid is still stable, but we have to check the pH level, because the pH level is an important factor affecting the stability of nanofluid. And then this is a table of comparison silica SLS and silica by the time for 5 days. And from the table we know that for the nanofluid without SLS, the decrease is approximately 3%, and for with silica SLS is only 1%. The lower decrease in pH with time may indicate that the silica nanofluid with SLS is stable than without SLS. The decrease in pH may be caused by condensation reaction of surface silanol groups with the remaining orthosilicic acid in water. And then this is a reaction of silanol groups and condensation reaction. And then the presence of SLS in the solvent may hinder the direct contact between the surface silanol groups and the orthosilicic acid. This may be the reason why the pH of silica nanofluid with the presence of surfactant only decreases slightly. Then, for proof, the stability of silica nanofluid, beside from physical appearance and pH level, we have to measuring zeta potential value. The zeta potential value of plus minus 30 mV is regarded as a critical value for evaluating the stability of the nanofluids. A lower zeta potential or less than 30 mV leads to particle agglomeration, whereas a higher zeta potential more than 30 mV can maintain stability. And in this graphic, we compare zeta potential value of silica, SLS nanofluid, and silica nanofluid for a day and after a month. For silica nanofluid, in a day 1, zeta potential value is minus 24.2 mV, and then after a month it's to be minus 39.033 mV. And then from the result zeta potential value, it can be said that in a day 1 silica nanofluid cannot classified stable because zeta potential value is less than 30 mV, but after a month silica nanofluid can be said that it's stable because it have zeta potential value more than 30 mV. It's compared to silica SLS nanofluid. In a day 1, zeta potential value is minus 53.233 mV, and after a month it's to be minus 61.3 mV. And then it can be said that silica SLS nanofluid is stable. The reasons why silica SLS stable is because the presence of SLS also has a function to stabilize colloidal silica through steric stabilization. Then, to find out there is no aggregation, distribution particle was measured. Beside of zeta potential value, particle size is a important factor to know that nanofluid is still stable. And then for a silica nanofluid, in day 1 the highest peak is 4.849 nanomicro, and then after a month it's to be 5.919 nanomicro. And then for silica SLS nanofluid, in day 1 the highest peak particle size is 5.616 nanomicro, and then after a month it's to be 7.531 nanomicro. And then for comparison silica nanofluid and silica SLS nanofluid particle size, it's less than 10 nanomicro, and it can be classified as nanofluid. And then this table observation the stability colloidal silica to time. We measuring viscosity value and particle size value for a month, to know the stability colloidal silica. And then the relationship between viscosity and particle size is that viscosity increases with increasing particle size. This increase maybe indicate the growth of particle. We can know from the table, and then we know that from the table is silica SLS have a viscosity higher than a silica nanofluid. It may be because we add surfactant in that nanofluid, and then the nanofluid solution become thicker, and it may be the reason why silica SLS have viscosity value higher than a silica nanofluid. Finally, the conclusion of this work is the addition of the SLS surfactant can increase the stability of the silica nanofluid. It can be known from zeta potential values of silica SLS is minus 53.333 millivolt, and the zeta potential values of silica is minus 24.2 millivolt. The particle size for silica nanofluid and silica SLS both are 4.849 nanomicro and 5.616 nanomicro. So it can be indicate that the particle size of silica nanofluid still can be classified as nanofluid. And then the last but not least, sorry for all the mistake that I have made during this explanation. Thank you for your attention.